Hello, everyone. Welcome to this new appointment of the fourth under 40 e-lecture series on combustion. It's a pleasure for me to introduce the speaker of today's speaker, Professor Alessandro Stagni, who is an assistant professor of chemical plants at Politecnico di Milano since June 2017. In 2016, he obtained his PhD in industrial chemistry and chemical engineering at Politecnico di Milano. He has also been a visiting PhD student at Stanford University in 2015 and visiting researcher at Technische Universität Darmstadt in 2019. His research activity deals with the chemical kinetic analysis of reacting systems at different levels, from the development and reduction of kinetic mechanisms to their application in CFD computations. Within the current energy transition scenario, his research has recently expanded to the investigation of the combustion of ammonia as a carbon-free energy and hydrogen carrier. And we will hear from him today about combustion of ammonia. So, Alessandro, thank you for accepting our invitation. It's a pleasure to have you here, and I leave you the virtual floor. Thank you.
Thank you, Salvatore. It's really a pleasure for me to be part of this series of e-lectures by the under 40 researchers in combustion. So when I was invited, I had to decide what should I talk about, and maybe the most how can I say, the biggest core business of my activity in the last 5 years has been chemistry of ammonia in all of its facets, from a theoretical side, kinetic modeling side, and partly experimental sides, thanks to the collaboration with other institutions. So in these 50 minutes, I will try to provide an overview of state of the art, where we have arrived, and especially which are the next steps where we want to go. And this is the outline of what I'm going to present. A brief introduction about the motivations behind my work, why ammonia has become so important in the latest 10 years. Then I will split my contribution into two parts. The first one dedicated on ammonia pyrolysis and oxidation, ammonia as such. And second, ammonia in co-firing mode, so ammonia combined with other fuels, and so this topic connected to the fuel flexibility issue. And finally, conclusions and the next steps. So in the latest 10 years, I mean, I've done several combustion symposia since 2014 to 2022. And what I've been experiencing is that the interest, the number of publications, number of papers of ammonia has exploded. Why this? This is connected to the increased interest on ammonia as an energy carrier, as a smart energy carrier. And this is connected to the increasing availability of renewable sources, so wind, solar, tides, and so on, which are intrinsically discontinuous. So in order to solve this issue, the chemical storage has become more than a possibility. And because of its properties, its physical properties, the high energy density, the easiness of transportation, and especially its carbon-free nature, ammonia has become, you can say, one of the top players of the energy transition. So starting from renewable energy, we can synthesize ammonia, and then when energy is needed, we can burn ammonia. Okay, so it's the same concept as a battery, basically. The second reason why ammonia has become very important in the latest years is because of its historical use in the chemical industry. It's been 100 years, more than 100 years, that ammonia is being used in other fields, totally different from combustion, for example, fertilization. So there are a lot of established production technology, and it's used, as I already said, for non-combustion application or other technologies which are also familiar to us, like thermal denox for the abatement of nitrogen oxides. So I would like to provide an historical overview of how our research started in ammonia. It actually started, I would say, 6 years or so ago in a project which was not 100% focused on ammonia, and it was basically targeted at the formulation of the next generation steam cracking furnace. This was called Improve. It ended in 2020, and its two major targets were 20% higher energy efficiency and 25% less greenhouse gases and NOx emissions. And this was a complex problem which needs to be faced from several parts. So to reach these targets, we had to use a novel material, novel design, novel modeling, and novel alternative fuels. And as you can imagine, the task of our unit, Polimi unit, was focused on these 4 targets. So we were trying to model for the chemical behavior, the combustion behavior of alternative fuels, so primarily biogas and bio oil. When we put bio at the beginning of a word, everything seems amazing because in this case we have 0 net CO2 emissions from a life cycle perspective. We can zero the dependence on fossil fuels, and we can use waste materials. But there are also disadvantages, as you can imagine. The composition of biogas, of biofuels, very often contains a lot of compounds which are tremendously or harmful for the health and for environment. This includes sulfurated compounds, chlorinated compounds, volatile organic compounds, and especially organic nitrogen, which can be a significant part of the composition of a biofuel, as you can see from the pie chart in the bottom right. So if we need to model the behavior of biofuels, we need to model the behavior of everything which is included in biofuels. And so among them, we started modeling ammonia. We didn't start from zero because ammonia has been already studied, especially for the high temperature pyrolysis and oxidations since the 80s. Chemistry of nitrogen was important for other reasons, for rocket fuels, and so on. Recently, starting from 2010s, the number of fundamental studies on the oxidation chemistry of ammonia has exploded. So the number of experimental campaigns is exponentially increased. From the other side, also the number of theoretical studies on specific reactions. On the other side, the current interest is no longer limited only to high temperature pyrolysis and oxidations, but also to less conventional conditions, which we can say, for example, low temperature and diluted conditions. And so this is basically the timeline that we followed in these years. We started from the gas phase oxidation of ammonia. Then we continued with the study of ammonia co-firing, first with methane, and then with the hydrogen. With the last question, which I will do several times today. Are we done with ammonia kinetics, or where do we want to go? So let's start from the first topic, ammonia pyrolysis and oxidations. As I said, there are a lot of studies in for experimental and theoretical, which can support us in the development of a predictive kinetic model of ammonia. And in order to build a comprehensive model, we have to consider all the experiments, all the theory, and understand where these literature data are actually lacking, so that we can continue our study with further experiments and further theory. So in this way, we integrated a continuous improvement workflow in the development of ammonia kinetic mechanism in such a way that as soon as new theoretical calculation and new experiments are performed, we can include them in our modeling activity, and then we can further refine our model. In this way, we can also decide which are the most critical operating conditions, where the experiments are most uncertain, where theoretical calculations are most uncertain, and then we can design further experiments and theoretical calculation and perform them either alone or with, in collaboration with other institutions. So the first step was a literature collection of a huge amount of data. And this is a chart for the left side regarding a series of data sets that we collected over the years for ammonia oxidation experiments. While on the right side, you have the same for ammonia hydrogen with a different coordinate, which includes, in this case, the blending ratio. And one of the most critical conditions was ammonia, pure ammonia in low temperature and, as I said, very lean conditions. So we decided to start further experiments in these conditions. In Polimi, we don't have experiments, so experimental facilities. So we perform this activity in collaboration with the external institution. So in collaboration with the CNRS in NC, we performed a combined experimental and modeling study. And in order to cover the whole temperature range, we used two different reactors. The first experimental device consisted of a quartz Jet reactor, which was kept at a constant temperature. And geometrically, it can be thought as a spherical vessel where a preheated fresh mixture is injected and high turbulence is generated inside the reactor so that homogeneity can be assumed for both composition and temperature. We can study a limited set of temperatures due to the quartz mechanical resistance, so going from 500 Kelvin to 1200 Kelvin. Helium was used as a balanced gas. And in this way, through the Jet reactor, we could explore the low temperature behavior of pure ammonia. The second setup consisted instead of a flow reactor, able to reach higher temperatures up to 2000 Kelvin, and it consisted of basically of a tube made of recrystallized alumina. It was specifically designed to approximate segregated conditions so that from a modeling point of view, we can model it as a plug flow reactor. We imposed a fixed temperature profile to the reactor walls such to keep a set point temperature, as you can see here, for approximately 50 milliseconds. The reactants and products were identified and quantified using 4 analytical techniques, complementary between each other. The first one was an online gas chromatography for the quantification of this species plus hydrogen during ammonia oxidation in the flow reactor. The second one was online mass spectrometry to detect NH2 and ammonia, N2, H2O, and oxygen. The third device was this continuous wave cavity ring down spectroscopy for ammonia. And the last one was NOx analyzer, where nitrogen oxides were measured by chemiluminescence, while NO2 was calculated by difference. All of these could guarantee a relatively high accuracy, as the maximum relative uncertainty of the measurements was around 5% according to the instrument. On the other side, we use experiments and theoretical tools to support experiments. Indeed, in the last years, theoretical kinetics has undergone significant improvements because the accuracy has grown so that the rate constants can be accurate by a factor 2, which is not which can change everything, as we will see later, but is anyway the state of the art. Also, since 2010 or so, a lot of literature has become available for the calculation of specific ammonia-related rates. On the other side, when we calculate each of these reactions, the calculation of each reaction involves a lot of steps. This is very time-consuming, and this is very often very manual. This is a process that involves many steps, and so is error-prone, and needs to be speed up and automatized and standardized. When we calculate the rate constant, as I already said, there are a lot of steps. An ab initio phase, which can be summarized in this chart, then a transition state theory, and then master equation. In order to collect all of these steps and to make everything as automatic as possible, in 2019, this automatic tool was released, S2KTP, by Professor Cavallotti in Politecnico di Milano and co-workers. This was a collaboration with Steven Klippenstein at Argonne National Lab in the US. The target of this software was obtaining rate constant within a factor of 2, which is very high, with respect to experiments at temperatures relevant for combustion conditions. So, in this way, S2KTP works with a series of steps in series, so that the state-of-the-art ab initio and kinetic theories can be adopted, if possible, but it's not always possible, as we will see later, without multi-reference methods, and preferring robustness over computational efficiency. So the objective is obtaining a constant, even if the calculations are very time-consuming. The advantage is that the needed knowledge is reduced to a minimum, but it's still present. But we need a minimum knowledge of electronic structures, kinetic theories, and so on. Several reaction classes are implemented, among which H abstractions, additions, isomerization, beta decomposition, and barrierless reactions. Once we have a lot of experiments and the theoretical calculations, we can assemble a kinetic model. Kinetic model which was built following the principle of the crack kinetic framework. So in a modular way, so that we can consider the part of the mechanism which is actually of interest to us, so hierarchic way, and with the principle of a generality. So we want a model that is which is reasonably predicted in the whole operating range. And we started in a modular way several years ago by updating the core mechanism. So hydrogen mechanism and C1, C3 mechanism. Then in 2018, we updated the NOx mechanism. Then we updated the ammonia mechanism in 2020. Behind this, we also updated thermodynamic data considering the latest calculation of Burkhardt and ATCT database. Overall, the kinetic model of ammonia is relatively small if we compare it to upper hydrocarbons. It's only around 30 species and 200 reactions. So it can be used in several applications, even multidimensional. The first part of our work, when we designed when we were assembling the mechanism of ammonia, was a theoretical evaluation using the tool that I already described of the most important reactions, which were selected according to sensitivity analysis and uncertainty analysis of the available rates in literature. So we consider the initiation reactions, so the thermal decomposition of ammonia and the H abstraction by O2, the remaining H abstraction reaction by the major abstractors, so HO2, H, OH, and O, and the decomposition of H and O. And the results were quite interesting because on the one side, we got confirmation of the validity of several literature rates. For example, the thermal decomposition of ammonia here and the H abstraction by OH. So our predictions were in agreement with the experimental data. On the other side, we had a lot of differences because as you can see here, the H abstraction by O2 at the bottom left, in this case, is plotted as the reverse rays. This is totally different from what is available in literature. The literature rate used until, I will say, 2018, 2019 is the dashed line here by DIN. When we perform our calculation, we obtain the continuous line. So a kinetic rate which is order of magnitudes higher, especially at very low temperatures. Similar results, although not so breakthrough as the H abstraction by O2, were obtained for H and O, and we were able to fit a rate which is the continuous line on the bottom right part. After we re-evaluated all the rates, we tried to assess, to quantify the importance of these rates in the kinetic behavior of ammonia. And we started from low temperature oxidation. We collected data in NC in diluted and very lean conditions, as you can see from the equivalence ratio here. And when we try to model this data, we can see that the state-of-the-art literature models in 2018 by Glarber, but also other mechanisms were predicted an earlier reactivity onset compared to the experimental data. When we try to model the same with the new model, we were able to reasonably follow the experimental trend, both for ammonia consumption and nitrogen oxides formation. So we started asking ourselves, why this? And the reason, the main reason is to be attributed to the H abstraction by O2, which I showed you in the previous slide, which shows a very interesting behavior. If we see here the sensitivity to ammonia mole fraction, so the positive bars don't favor the consumption, while the negative bars favor the reactivity. We can see that, interestingly, this reaction has a positive effect on ammonia mole fraction, so a negative effect on reactivity. This could sound counterintuitive, with why initiation should go in the opposite direction than reactivity. Well, the reason is that this is an equilibrated reaction, and if we have very lean conditions, we have an accumulation of HO2. So for equilibrium reasons, the reaction goes in the opposite way. So in diluted conditions, we have that the H abstraction by O2 goes in the opposite direction, as you can see here from this arrow. If we consider the rate by Din and Bozzelli, the previous rate, which was much lower, this reaction wouldn't have had such a big impact, and so the reactivity would have been mispredicted by, as I already said, 100 degrees or similar. Then we moved at a higher temperature. We obtained flow reactor data still in very lean conditions in NC, and we can see that, first of all, the model is reasonably able to predict the consumption of ammonia. Second is that the NO formation is driven by the composition of HNO, which was one of the reactions calculated. Results are reasonable, except we just have an over-prediction of 20–30% of NO, but this needs to be reconciled also with the remaining data, literature data, as well as the data that I will show you later for the other datasets. And these are the other datasets. Our model needs to be general, so needs to be good, not only on the data that we collect, but on the data that others collect. So we validated our mechanism for ignition delay time and laminar flame speed. And results are very good. I mean, we have a very good behavior in a wide range of temperatures and pressures, and equivalence ratio. And as you can see here, the dominating reactions are still those that we have recalculated in the first part of our work. So our mechanism is general. So the question is now, are we done? Is there anything to be explored? And this was the question that we did after we completed this part of work. And then the answer was, not yet. We need to go further. Why this? If we consider the low temperature oxidation of ammonia, we can very easily identify, both in our experiments and in experiments performed by other people, a very important compound, which is H2NO, so the nitroxide radical. We can see here from sensitivity analysis that the H abstraction from H2NO by NO2 and O2, for example, are the key to the regulation of reactivity. Why this? Because as you can see here from a flux analysis, the ammonia radical provides H2NO, then H2NO is abstracted by a series of radicals, providing HNO, and finally the nitrogen oxide. These are reactions occurring only at low temperature, so H2NO can be considered as the door to low temperature oxidation of ammonia. Also, if we analyze all the data, we can realize that the worst prediction of our model are present at high pressure, as you can see, and the low temperature conditions again. And here we can see, if we perform sensitivity analysis, that H2NO is still the key compound. So we want to analyze this step, how we go to H2NO to HNO. And so we decided, together with Professor Cavallotti, to analyze to investigate through a first principle approach, the H abstraction from H2NO by the major abstractors which were identified by a sensitivity analysis. And they were O2, NH2, HO2, and NO2. And this was not immediate from a theoretical point of view, because in the case of H2NO, we need to study this particular class of reactions, which is radical-radical H abstraction. And this reaction class is kind of peculiar because the electronic structure changes significantly between reactants and products. And this means that when the two reactants are considered, the electrons are in their respective orbitals, which are separated at long distances. But as the molecule approach get closer and closer, the two electrons combine into a single molecular orbital. And we go from a potential energy surface defined as a singlet d radical to the formation of a molecular orbital. And so the two electrons with the opposite spins are combined. And this leads to a strong interaction between them, which is called the electron correlation effect. And so, since the structure also changes significantly between reactants and products, the system shows a strong multi-reference character. And to describe multi-reference reactions, which means that more than one electronic structure is needed to describe the system, we need to define a suitable theoretical approach. So it's not the classical approach which was already implemented in S2KTP. And so we defined this protocol. We used the S2KTP code to automatically determine the rate constants, starting from these first principle calculations with a multi-level approach. So a level 0 geometry optimization for reactants and products performed at a lower level, and then a grid scan to determine gases for the transition state using DFT geometries. Then, after determining level 1 geometries, we determine the structure at a higher level of theory, and we did this at a CASP82 level. So using a minimal active space on the previous gas that we already obtained. And then on this multi-reference structure, so more than one electronic structure is needed, we computed energies with two different approaches, because we wanted to validate, we wanted to verify that they were getting to the same values. Approach A was still at the CASPT2 level, but with a large basis set and the largest possible active space. While the approach B was at the couple cluster level, where the excitation energy between the singlet and the triplet, and the doublet and the quartet was evaluated through CASPT2. And to determine finally the rate constant, we used the so-called three transition state model, and we determined the van der Waals rate constants, van der Waals reactants and product wells, and then we solved the master equation to obtain the final value, value of the rate constant. Then I already told you that we try to use two different approaches to evaluate the energy barriers. If we use a standard approach, so we determine the energy at the DFT level, then energy at the couple cluster level, we obtain these values of energy barriers. For all of this reaction, we obtained this value. This is T1 diagnostic, and the high value of T1 diagnostic means that the reaction shows a strong multi-reference character. If we use this approach, the basic approach already implemented in the code, to evaluate the enthalpies, then we will see that this approach is very accurate and the values are corresponding to what already available in ATCT within the uncertainty range. On the other hand, if we properly account for the multi-reference nature, we use approach A and approach B, we find these energy barriers. You can see that especially for H abstraction by O2 and H abstraction by NH2, there is a huge difference in terms of energy barrier, which is 3 to 5 kilocal per mole, and this can completely change the value of the kinetic rate. Why this happens? Because of multi-reference character. And the structure you see significantly changes from approach A, basic approach, no multi-reference, and approach B with CASPT2. This is sample H abstraction by O2 from H2NO. And as you can see here, there is a different distance between the oxygen atoms with approach B, where they are much closer, compared to approach A. This is because if we consider the two different electronic configurations, then there are some difference in the optimization of the structure of the system. And if we consider the multi-reference character and we want to estimate the uncertainty of these theoretical methods, then we can say that the remaining uncertainty is 1 kilocal per mole, which is about a factor 2 at 1000 Kelvin, which is compatible with the state of the art. And so we reevaluated these 4 reactions, and starting from H abstraction by O2, which is the only reaction for which theoretical data were already available. They were evaluated by Song in 2016, and then adjusted by Glarberg in 2018 by correcting the activation energy by 2.5 kilocal per mole. As you can see here, our reaction rate, which is the continuous line, while the gray area indicates a factor 2 by our kinetic rate, is compatible with the adjustment performed by Glarberg on Song data. So this was quite satisfactory. On the other side, if we compare our kinetic rate with the literature, the few literature estimations available for NO2, NH2, and H2, we can see that there is a lot of difference with such estimations. So once we have evaluated these rates, our question was, what's the impact of these rates on the model? And so we introduced the H abstraction by different radicals on H2 and NO in our model. For the high temperature data, there are no different. So the model was still reliable in a wide range of temperature and pressure for ignition delay time, laminar filling speed, and the flow reactor calculations. So the mechanism is still general. The problems was mostly involved in mostly at low temperature and lean conditions. Here there were significant difference. The mechanism still preserving generality, although there is a delayed onset at lower temperature, but on the other side, there is an improved description of ammonia consumption at high pressure. This is a flow reactor on the bottom left part, which is operated at 30 bar and was done by Song in 2016. There are three major paths to NOx and N2, which are basically the ammonia radical reacting with NO2, NO, and HO2. And with each of them, there is one propagation channel and one termination channel. For both the propagation channel of HO2 and NO2, the bottleneck of all of these is H2NO, as I already said. So the question was, which is the actual impact of the H abstraction? And we need to do kinetic analysis to perform this. So with sensitivity analysis, we found out that the first three H abstractions actually counteract reactivity, as you can see from sensitivity analysis. Why this? Because they provide products more stable. Okay, on the other side, the H abstraction by O2 favors reactivity, as you can see here, because then HO2 propagates to OH via NH2 plus HO2. Okay, and H abstraction by O2, so which is the last one, is the actual driver of reactivity. On the other side, there is a smaller inhibiting effect of HO2 and NO2 as abstractor from H2NO, which is not even reported here. The major reactions counteracting reactivity are related to H abstraction by NH2, as you can see here, which is the first one, which is the current impact of uncertainty. And to do this, we perform a brute force sensitivity analysis to ignition delay time. So basically, we calculated these four reactions. What happens if we multiply or divide each of these reactions by a factor 2, which is anyway within the experimental uncertainty? And we selected some literature data by Pochet in 2019, and we calculated ignition delay time in rapid compression machine, so considering the volume history, by multiplying or dividing each reactions by factor 2. And the results are quite interesting because for HO2 and NO2, there was not such a big effect. And so the maximum deviation was 30% from the values we calculated the reaction. On the other side, if we consider ignition delay time by varying the H abstraction by NH2 and O2, we can see that the ignition delay time may vary by a factor 3 or by a factor 5. So the prediction of the model can be completely wrong. We have also to consider that this analysis shouldn't be done only for H2NO, for these four reactions, because there are a lot of other uncertain reactions in literature. And we will need to do this similar analysis also for a lot of other termination or propagation channels. We should consider also that not only these data sets should be considered, but a lot of other data sets in literature, so we can easily understand that the problem becomes very, very complex and complicated. And so the conclusion of this part is that, okay, we have very accurate kinetic rates, we have very accurate experiments, but optimization is a next necessary follow-up of all of these in order to reconcile the predictions. Okay, once the part related to ammonia pyrolysis, to pure ammonia combustion was let's say, completed, we moved to ammonia oxidation in co-firing mode. Why this? Because energy transitions means flexibility. In order to optimize the resource exploitation, we need combustion of several fuels very often. And on the other side, ammonia co-firing can strongly improve the combustion features of ammonia, which are particularly weak in terms of autoignition delay or laminar flow propagation and so on. Second, and third, ammonia is a hydrogen carrier. So we can obtain hydrogen starting from ammonia itself. So we can move from the direct use of ammonia, which I've studied so far, to the indirect use of ammonia with prior decomposition to hydrogen, and ammonia co-firing with other energy carriers, which can be obtained from renewable sources. If we consider ammonia co-firing in particular, we have shown that in the past that sensitizing effects have been shown with methane, with other fuels. But the chemistry of these interactions has been investigated not in detail until a few years ago. So the next step of our research on ammonia has been the experimental and kinetic modeling characterization of ammonia co-firing with small hydrocarbons. So the first part is related to ammonia methane, and the second part to ammonia hydrogen. Regarding methane, you know that ammonia combustion properties are very weak, and here you can compare the laminar flow speed with methane and the laminar flow speed with ammonia. So there is a factor 5, 6, or even more. So the solution is we can blend ammonia with conventional fuels, which can still be obtained indirectly from renewable sources. So we are still CO2 neutral from a life cycle perspective. We want to study ammonia methane, we should start from ammonia and nitrogen oxides interaction. Why this? Because in the past, sensitizing effect between methane and nitrogen oxides were already shown. Basically, what happens if we have nitrogen oxides or nitrogen dioxide with methane, we have that NO2 reacts with the methyl radical, providing CH3O, and then hydrogen CH3O decomposes, providing reactive hydrogen radicals, or NO reacts with the methyl peroxide, providing again CH3O and again hydrogen radicals. So the net result is that the presence of nitrogen oxides can speed up methane oxidation, especially at low temperature. What happens if we move from CH methane NOx interaction to methane ammonia? Well, we did experiments again with the help of CNRS-9C for the experimental part, and you can see that the early reactivity is again observed, although at a lower extent compared to ammonia NOx. So we have an anticipation reactivity of about 80 Kelvin at lean conditions and smaller at 10 Kelvin at stoichiometric conditions, no anticipation in rich conditions. And the interesting thing is that this was reasonably predicted also by the kinetic model. Kinetic model that wasn't always showing stationary results. I mean, if you can see here the dashed line, this was because our kinetic model, our CSTR model was not providing stationary results, was providing oscillating results, but this is part of combustion in a perfectly still reactor. We have already shown in the past, in previous works, that oscillating combustion can be established, and with our pleasant surprise, the kinetic model was still able to predict the species formation in the oscillating combustion. Why ammonia sensitizes methane oxidation? Well, if we perform kinetic analysis, we can understand what's happening. Basically, even if we have small amounts of ammonia, ammonia becomes NH2, and then NH2 provides nitrogen oxides. And even small amount of NO sensitize the oxidation process and anticipate the reactivity onset. So ammonia triggers the interaction, the reactivity of methane by interaction with the NOx, but NOx are obtained by ammonia itself. This is very, very interesting. And the amount of sensitization results from the competition between branching and termination path. Again, here we have the key role of the HO2 radical as in the pure ammonia. As you can see, that termination is important also for the H abstraction, for the reverse H abstraction by methane, which is the first reaction here. Okay, basically a catalytic cycle is established, and we move from methyl radicals to the more reactive OH radicals, and methoxy radical, which then decompose to formaldehyde and hydrogen radicals. On the other side, at high temperature, we did experimental and modeling study in a flow reactor to understand if anything is changing, but no significant change in reactivity is observed moving from ammonia to methane. So basically what happens? It happens that ammonia burns on its own, methane burns on its own, and if you can see here sensitivity analysis to methane, you can see that the important reactions are those related to ammonia, those related to methane, but there is no mutual effect, and this is due to the fact that we are dealing with very high temperature compared to the past situation. And finally, we move to ammonia hydrogen. Why this? Well, ammonia is intrinsically a hydrogen carrier, and hydrogen can be obtained by thermal cracking or catalytic cracking, and there is a whole field of study related to this. The good thing is that if we can control cracking, we can control the fuel blend, and we can obtain the fuel blend with the desired reactivity features. And so these having ammonia hydrogen mixtures become a potential keystone for the decarbonization and especially for the fuel flexibility. So we can choose between something in the middle between having a higher energy density and an easiness of transportation and good autoignition and flame speed properties. And we can go everywhere between pure hydrogen to pure ammonia according to the application. What happens if we study ammonia hydrogen mixtures? Does everything proceed independently, like I showed you in the past slide for ammonia and methane, or is there any chemical interactions? Moving at low temperature, we started from low temperature, still together with the help of CNRS and C, and we studied ammonia hydrogen oxidation with different amounts of hydrogen. In this case, at low temperature, we observed a linear reduction of the conversion onset with the hydrogen amount. You can see here in the bottom right, the half conversion temperature, which is linear, but except for the smallest hydrogen amounts where this derivative is faster. Okay, if we add small amounts of hydrogen, we change the reactivity of ammonia more rapidly than if we add higher hydrogen amounts. Especially if you can see here, as you can see here from the bottom right chart, ammonia is consumed before hydrogen. Why this? Well, because hydrogen is an intermediate of ammonia oxidation. So as you can see here, hydrogen is first formed as a byproduct, as an intermediate of ammonia, and then it's consumed. What happens to the nitrogen fate? Well, the two major products which were measured in this condition were nitrogen, molecular nitrogen, and nitrogen oxides. And you can see that even small amounts of ammonia results in nitrogen oxides generated from ammonia. So it's not thermal NOx, just to say. Especially the predictive nitrogen oxides was non-monotonic with the temperature. This is in principle unphysical because nitrogen oxide should increase with the temperature. So we asked ourselves why our model is predicting this behavior while the experiments are monotonic or at most flat. And we try to understand the evolution of nitrogen oxides along the reactor length, as you can see here. Here I plotted the nitrogen ammonia consumption here and nitrogen oxide formation here as a function of the reactor length and also overlapping the heating history. This was for 3 different nominal temperatures. And as you can see here, the problem was related to the heating history. So according to the specific heating history, which is not strictly correlated to the nominal temperature, the mixture can ignite sooner or later. And this happens not in the constant temperature part, but in the part before the constant temperature one. And so the predictions are particularly sensitive to the specific heating history. Okay. What happens at low temperature? At low temperature, we should also consider the possible formation of N2O. N2O has become a very strong requirement for kinetic models because as a greenhouse gas effect 300 times stronger than carbon dioxide. We try to model literature data in just a reactor. This data, I think they were performing KAUST, and we try to understand the nitrogen phase in terms of competition between nitrogen oxides and N2O. And you can see that N2O and NO are basically in strong competition, and this is due to the first reaction. So NH radical plus NO giving N2O plus H. According to the rate of this constant, N2O is favored and NO is decreased. The problem is that if we consider these two first reactions, these two most important reactions, you can see that this can have this can have an effect here, but an opposite effect in previous predictions. So we need to reconcile the different sets of data. Moving to high pressure, just to complete the picture, we studied the rapid compression machine at a low temperature with variable amount of hydrogen. And here you can see that the behavior for the ignition delay time is totally nonlinear. Even small amounts of H2, as you can see here, 1% or 5%, totally boost the ignition delay time. If we consider sensitivity analysis, again, we see that this nitrogen chemistry driving ignition. And as you can see here, one of the key role is played by the H abstraction by O2 from H2NO, which is the one we recalculated. At high pressure, finally, we have a high importance of a nitrogen dioxide, because then nitrogen dioxide reacts with NH2 with a propagation channel and a termination channel, and then it regulates reactivity, becoming basically the most important reaction. Finally, flame propagation. Hydrogen, we found by modeling all the literature data, we found confirmation that hydrogen provides a more than linear boost to laminar flame speed. And this is because the radical branching is increasingly driven by these two red reactions, which are the H abstraction from H2. But you can see that the accuracy, if you consider the last reaction, this reaction is slows down the laminar flame. On the other side, it favors the formation of nitrogen oxides, which were in the past data set. This accuracy becomes partially antagonistic. So all of these examples are to confirm that optimization is still an important part at the end, and we need a trade-off between the accuracy of all the data sets. So coming to the conclusions, we've tried to face the problem of ammonia with a threefold approach based on ideal reactors, quantum chemistry, and kinetic modeling. With the adoption of a continuous improvement workflow allows to keep the mechanism always up to date and to constantly improve it according to the experimental and theoretical discoveries. ab initio tools can be extended to fill the lack of knowledge, in our case, in the lean conditions. And we re-evaluated the H abstraction from H2 and NO, and we set up a protocol which can be also used for other radical H abstractions. And finally, by developing the mechanism with a modular way, we can directly couple it with the C0, C3 mechanism and study the interaction of ammonia with other fuels. So again, for the last time, are we done with ammonia kinetics? There is a lot to be studied yet. We have completed the part completely. We have arrived to a very good point for the gas phase oxidation and the interaction with the basic fuels, so methane and hydrogen. But in spite of these, the theoretical and experimental uncertainties, as we show that they result in very strong sensitivity in the prediction of the kinetic model. Several datasets are antagonistic in their predictions. So if we improve it, the second one gets worse. And so an optimization step is needed to reconcile prediction and experimental data. And last point, fuel flexibility implies a wide palette of renewable e-fuels. This involves ammonia. This involves not only hydrogen and methane, but also dimethyl ethers, methanol, oxymethylene ethers, and so on. So we have more degrees of freedom to tailor-make specific blends according to our needs, but then we have a lot of chemical interactions to be investigated. Before concluding, I would like also to acknowledge the collaboration of our group, together with Tiziano Faravelli and Carlo Cavallotti, with the Siena residency for regarding the part regarding the experimental study for pure ammonia, ammonia hydrogen, ammonia methane, and then the cooperation of Prism Lab, so Christine Roussel and Pierre Brequigny for the part related to the ammonia hydrogen. And also, of course, I would like to thank the financial support of the Improved Project for funding all of this activity, together with the cost action smart cats, so chemistry of smart carriers, smart energy carriers and technologies, which was concluded more or less, say, 4 years ago. And also, I would like to thank you all for your attention, and I'm open to questions from all of what I've shown here. Thank you very much.
Thank you. Thank you, Alessandro, for this interesting talk, dense of information. Yeah, I would like to open the Q&A session. So if anyone in the audience has a question, please raise your hand and yeah, feel free to ask. Okay, if we have the first question will be from Marco. Please, Marco Lubrano, go ahead with your question.
Hello, Alessandro. Can you hear me?
Hi, Marco. Yes, sure.
I have actually two questions. The first one was more like a curiosity about the first part that you have shown on ammonia oxidation, where you have shown that the abstraction by oxygen inhibits the reaction rather than promoting it in the jet-stirred reactor.
Yes. Yeah. 1 second. Yeah.
Yeah, but this is true also with other mechanisms, or it is due to the fact that with your new calculated reverse reaction, the reverse reaction is much higher than the other mechanism. So I mean, what is my question? Is this a general behavior also if you have tested other mechanisms? I don't know. Or this is a specific feature only for your model because of this different rate constant?
Yeah, so this is actually the reason is the second one, because when we recalculated the kinetic rate, this was much higher than what is available, for example, by Dean and Bozzelli, which was used in a lot of mechanisms until 2018, 2019. And if we use this dashed line, then you can see that this reaction will no longer have this behavior. But and this is why, if we use, for example, an established literature mechanism, reactivity will be anticipated because this reaction will no longer hinder the reactivity. Okay, the problem is that we form a lot of HO2. since we form a lot of product, then the reaction goes in the opposite direction.
I see. Okay, thank you. And the second question was about your last slide, where you have shown actually a ship powered by ammonia. So my question is, I guess they blend ammonia with diesel or similar. So my question was if you have in your plans to also investigate the mutual interaction between ammonia chemistry and aromatics, because somewhere I read in a paper that when you do this, when you blend ammonia with aromatics, if you want to predict NOx, the sub-mechanism of aniline could be important. So my question was, it's in your plan or not? Because I know that you don't have the aniline sub-mechanism in your model, right?
In ammonia, no.
Yeah, so my question was if it's in your plan to investigate this.
Yeah, we are actually studying ammonia with aromatics also because, as you said, that there are effects of NOx, but there are also effects on soot. So it's an intricate interaction. It's a very challenging, but also very interesting activity, and we are working on it. It's because this also changes the also experimental works in the latest 3-4 years have shown that ammonia changes also the presence of ammonia changes the morphology of soot, and but this needs to be explained through the model. Then on the other side, as you can say ammonia aromatics can also affect the formation of NOx, but for this part, for this interaction, we have investigated less. We are mostly focusing on ammonia aromatics for soot.
Okay, I also think it's interesting. That's why I was asking. But yeah, okay, thank you. I'm done.
Thank you.
Thank you, Marco, for your questions. Okay, we have also Lorenzo that would like to ask you to ask Alessandro a question. So please, Lorenzo.
Yes, thank you, Alessandro, for the very nice results. And also, I have also like a couple of questions. One is about slide 39. Okay, it seems that okay, NO are, let's say, over-predicted in some way, but this is not something that is just, for example, for your mechanism, but I've seen that many mechanisms tend to over-predict NO. And do you know, like, why this happened, or what can be done to, because in the experiments, like in general, I've seen that in some papers, in other papers, that okay, these experimental NO are more or less always below the numerical ones. So I don't know if you have some.
This is true. You're right, and also if you remember in the few slides before when I showed you pure ammonia oxidation in the flow reactor, we had an over prediction by, I think it was 20-30%. The problem is that if we consider this data and we want to improve this data, then it happened. What we realized is that we got worse on these other data, for example, on N2O. So it's the short blanket problem, you know, and we need further theoretical studies on these key reactions on the one side. The second, we need to find the optimal trade-off. But I agree with you that I found several times that there were overestimation of NO, especially in this flow reactor conditions. And this overestimation is beyond the experimental uncertainty. I'm aware of this, but it was the best trade-off that we could find. Also excluding the right part whose oscillating behavior is related to the preignition inside of the reactor.
Okay, yeah, but I know that like it's not very like hard work. And I have like my second question is about experiments are generally carried out in quartz, let's say, chamber. Okay, but do you think that the material of the, let's say, the reactor can have an effect, interact, let's say, with the ammonia decomposition? For example, in a real combustor, in general, it is used steel. This can have like a different like interaction with respect with ammonia with respect to quartz, let's say. Do you think
this is a very good question? Also because we found important interaction effect. I think they were for sulfur more than ammonia, and they were totally anticipating the reactivity. To do this, when we studied the flow reactor conditions here, I think that we used two different, just a second. Yeah, I think we used two different materials for the flow reactor, and we obtained comparable results. Okay. So I would say that we're not, at least for the flow reactor conditions, they were not such a big difference, I would say. But I agree with you that you need a lot of care when you consider the wall reactions. I think that in the review by Glarbo in 2018, there was a chapter, a dedicated chapter on wall interaction with ammonia. And for a part of it is still an open question, in my opinion.
Okay, thank you very much.
You're welcome, thanks to you.
Thank you, Lorenzo, for your questions. And are there any more questions from the audience? Doesn't look like it. So yeah, I think probably time to close this session. And thank you. I would like to thank again our speaker for his for showing these interesting results and showing us that there's still a lot to do about ammonia in terms of the interactions with other fuels and pollutant formation like NOx and soot. So yeah, lots of research activities, lots of research needing. So yeah, thank you again, Alessandro, for your very nice talk. And,
thank you very much,
for
Salvatore.
accepting our invitation, and I wish everyone a good rest of the day. I'll see you soon for the next appointment next week of this lecture series. Thank you.
Thank you.
Have a good day, everyone. Bye-bye.
Bye.